right? So I think there's so many unknowns, and I hope our speakers will actually go into deep and increase your curiosity about the unknown over there as well. So before I start, I want to pay my respects to acknowledge and pay my respects to the traditional owners of all the lands that we are gathering around today. And it is a privilege to look at the skies as people have been doing for tens of thousands of years. And I would like to pay my respects to all the elders past, present, and emerging. So to start off with, we will have a talk about 50 minutes or so, and then afterwards we will have a Q&A session. And afterwards you can, of course, meet the speakers afterwards as well once we finish the talks. If you have something urgent questions, please raise your hands, and I'm sure the speakers will allow you to interrupt for briefly to go on to talks. So starting off, we will have Karl Glazebrook, professor at Swinburne. And he's been involved in HST as a young postdoc back in the day. So it's been a journey from looking from the optical wavelengths in space and coming into the near-infrared science. And Karl is leading the James Webb Australian Data Centre that I hope you've seen the banner outside as well, which we try to promote Australia's involvement in James Webb science and try to get people excited about the different things we do. We also have Colin, who's also a part of the JADC, who will be talking about more of his science and how we can look into different types of galaxies. Then we have Nicha, all the way from Melbourne University. It's a privilege to have you here as well, talking about the first and furthest away galaxies in the universe, and that'll be super exciting because that is also one of the main drivers of making the James Webb Space Telescope. So we will cover from the local into the high redshift universe, and starting off we will have Karl. Thank you.
Thank you. It's a great pleasure to be here for National Science Week. That should actually be better. So I think James Webb has been really in the news the last 2 months. I guess it's the astronomy story of the year. It's been a very nerve-wracking year with the launch in December and everything being commissioned until now. And we've had the first data for about 4 weeks now, so I hope to show you some of that. So this talk is going to be in 3 parts. I'll briefly tell you about why the telescope is so awesome, and believe me, it really is. Nicha will tell you about the very first galaxies, and in fact, within days of getting the data, we actually broke all the records for the furthest galaxies you can see. And Colin will come slightly closer to home to tell you about sort of galaxies in the infant universe, so kind of like teenage galaxies, and how we can look at them with new eyes. So this project is called Through the Looking Glass. It's early release science. We actually applied to do this. Our glorious leaders at UC Los Angeles, Tommaso Trey, we actually applied to do this in 2017. It's quite a while ago. And then ever since then, we've been waiting to actually get the data. So it's been a few years. And in fact, I've been waiting quite a bit longer because here's an article I wrote in 2012 when I was already waiting for the Webb, looking forward to the launch in 2018 back then. Not so much, but finally we have it. And the telescope was launched. So this is Christmas Day, last Christmas.
Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
So I was up at midnight watching this on 25th December.
Punching a hole through
How
the
many
clouds,
people in the audience were?
20 seconds into the flight.
That's
Good
quite a
pit
few of you.
program reported.
And of course I was going, don't explode. Although, actually, explosion was the least of our worries. So there it goes. This is actually the last view of James Webb as it heads off into the distant orbit. And in fact, we're never going to get another picture of James Webb unless Elon Musk flies by, because there's no cameras on the Webb telescope, because operate with those selfie cameras that can look back at it, because it operates so cold, anything like that just wouldn't work. And it's completely in the dark as well. So let's talk a bit about what an amazing piece of engineering the telescope is. So there's three key things I want to emphasise here. Three important aspects of the telescope, which makes it quite different from the previous Hubble Space Telescope. First, it's really big, and several times larger than Hubble. Then, it's really very cold, and that is quite important because the third important thing is it operates in the infrared light, and I'll tell you why. So, here's the comparison of the mirror with Hubble on the left and Webb. So you can see Webb is a 6-metre mirror, so it's a lot bigger than Hubble. Hubble mirror is like the size of a human. And because of that, you can see the mirror has to be segmented to built in parts. Because you have a big mirror, you can make sharper images. So here's a comparison of a star that was taken with Hubble and with Webb, and you can see the star is several times sharper with Webb. And then here's a comparison with a ground-based image of a star, one of the best telescopes. And you can see it's terrible. So you're probably saying, oh, Karl, why are you showing us boring pictures of stars? Oh, show you the good ones in a bit, and saving it. So why study infrared light? Okay, there's a number of reasons. Here's a picture. This just shows us a scene of nature comparing optical light, visible light, and infrared light. So on the left, you see some animals, meerkats and crocodiles. And then in the infrared, you see quite different scenes. This is wavelengths 2 to 3 times longer than you can see. So you can see the meerkats are actually glowing. Does anyone in the audience know why that is? Yeah, they have body temperature. They're warm-blooded, so they generate heat, and heat generates infrared radiation. Whereas the crocodile is cold-blooded, and that's why it looks so dark. So these wavelengths are sort of redder than we can see. This just shows the electromagnetic spectrum, which you all did in school, I hope. All the way from the gamma rays to the radio. Visible light we can see is a very tiny slice, and then the Webb telescope goes beyond that into the infrared. So there's two reasons for this. One reason is in a nearby universe, infrared rays penetrate through dust. And you can see this here. This is a nebula in our galaxy, and you can see the dark lanes. The dark patches are dust obscuring the nebula. And as you go further into the infrared, more and more of that gaseous structure is revealed. But the real reason Webb was built to be an infrared telescope is to follow the cosmic redshift of light, to see the early universe. Okay. So this takes some explaining. So let's have a go. So how many people have heard of the expanding universe? Yeah, quite a few. So the story is that as the universe expands and the galaxies go along with it, the radiation from distant galaxies also expands with the universe. This is a part of Einstein's theory. And as you can see, the light is stretched towards the red. So you have galaxies at further and further distances, the radiation becomes redder and redder. So maybe we should just run that again. So we stretch the universe, we expand it, the light is redshifted. You can see the longer wavelengths. And then you compare galaxies nearby, intermediate, and far away. You see that the further away you look in the universe, the more the light is redshifted. And also, the further away you look in the universe, the further into the past you're looking as well. Webb can see galaxies tens of billions of light years away, which means it's looking tens of billions of years back in time. So we're looking to the early universe, all the light is shifted to the red. This shows how that affects galaxies. This is now getting a bit complicated. The plot, we have a spectrum of a nearby galaxy, which means how the energy depends on the wavelength of the light, which I've coloured in there to show ultraviolet, visible, and infrared. And you can see that a typical galaxy nearby emits most of its radiation in the ultraviolet and the visible. But then if you redshift it, and so JWST is sensitive beyond 1,000 nanometers. Here's a redshifted version of that. So now we're looking back at a galaxy which is 3 billion years old. So for comparison, here's the current, whoops, I pressed the wrong button. All right, so today's universe is 14 billion years old. And then if we look at a galaxy 3 billion years ago, 3 billion years old, that's 11 billion years ago, it's redshifted like this. And then here's one, only 1 billion years after the Big Bang. All the light is redshifted in infrared. So if we look at this with Hubble Space Telescope, we're going to see nothing because all the light is too redshifted. So that's why we built JWST. And in fact, JWST doesn't just see infrared, it sees infrared in fine detail. It has 7 colours it can see in the infrared. And we'll see some of those pictures later. So, okay, it's big and complicated. Why do we put such a big and complicated thing in space? Well, you've already seen one reason. The first is you get sharper images in space because the effect of the Earth's atmosphere is gone. There's no blurring of the light. But the second reason is to do the requirement to operate in infrared. So here's another ground-based scene, seen in the infrared. This is the thermal camera. Can you work out what this is? Yeah. So why is the river water glowing? Yeah. You think water's cold, right? But water retains a lot of heat. This is a nighttime scene. And the water has retained the heat of the day, and the landscape has not. So you see the glowing water, you see a person there next to the lake, and you see the trees are very cold, but everything is glowing in infrared. Even the sky is at a temperature of a few degrees. You can see that on the top left there. Everything is glowing in the infrared. So trying to do infrared astronomy from the ground, it's like trying to do visible astronomy in the middle of the day. You're just overwhelmed by glaring light, which makes it impossible to see anything. So Webb has a range of infrared instruments. It has 2 cameras, near cam and near-IS. It has a spectrograph, which can actually dissect the light into those wavelengths you saw. And MIRI is a very fine infrared camera. So it's got a big complement of these infrared instruments. And just to show you why it's in space, here is like the world's deepest ever ground-based image taken at a wavelength of 2,000 nanometers. That's beyond what you can see. You see a bunch of galaxies there and stars. And then here's the same part of the sky with the James Webb Telescope taken recently. You can see the amazing difference. So this is like the ground, 30 hours, blurry, noisy image. With the Webb, you see much finer detail. You see a lot more objects. It's like 10,000 times more sensitive because it's in space and because the images are so sharp and because there's no thermal background emission. So to get to that point requires a lot of work. So firstly, Hubble was in orbit around the Earth, but Webb is being put a long way from the Earth because the Earth itself is a source of heat radiation, and so is the Moon. So you don't want all that horrible light pollution from the Earth to affect the telescope. So it's put in this L2 orbit, Lagrange 2, which is 1.5 million kilometres from the Earth, way beyond the Moon. And it has the advantage of that it's semi-stable and it stays the same distance from the Earth during the year. So the orbit is much colder. Second, it has this gigantic sun shield. So you've probably seen pictures like this. This thing that looks like a kite with 5 layers is actually very thin mylar screen, silver foil almost. And that acts to block the sun. So the side of the telescope with the mirror and the instruments will never see the sun ever again because it's blocked by this screen. It's like a factor 50 million sunscreen. That's the telescope cooled down to just 40 degrees above absolute zero. so minus 230 centigrade or something. So that's amazing, but it also means it's very big. It's like a 20-metre sunscreen, and we can't fit things this big in rockets. So this means that we had to have an insanely complicated telescope that would unfold. And we see this here. This little movie shows what happened after the launch. And in fact, this is why everyone was so nervous between like January and March. So this took place over 30 days. Basically, a little origami act of unfolding the telescope and deploying it, which had never been done before for a telescope like this. So this is a thing that really had everybody worried, not the launch, it was this, because there are 300 mechanisms here that had to work once, and if any of them didn't work, the whole thing would be a failure. So we were, all through January, we were just like tuning in for the daily update, everything's working, and it all worked. Unfolding these fabric sails is just an amazing achievement. So you can see the other side come out now. You see how the mirror is still not completely unfolded too. This is why, of course, the telescope took 20 years to design and build. And of course, everything was tested hundreds of times in the ground. But on the ground, you can't simulate the zero gravity of space. So that is always a concern. So here comes the secondary mirror out. And then it's 11 days after launch, deploying some thermal radiators. Primary mirroring, that means it's actually making the mirror. And I think they're getting close to the final assembly there. So there you go. That was the risky part of the mission. And then after a month of cruising, it arrived at this Lagrange 2 point and inserted itself into orbit. So you might think that was them working, but no. This giant mirror then has to be focused. And when you deploy it, it's within a few centimetres of the final position, but then the final position with all the mirrors aligned and focused, that has to be a precision at the wavelength of light, like 10 times the wavelength of light, so tens of nanometers. So it's like 1/10,000th of the diameter of the human hair is the precision with which these mirrors are aligned. This just shows the sequence here. First, each mirror is independently focused on a star, and then the segments are tilted to bring the images to a point, the same point, and then the segments are what's called phased, so that the wavelengths of light interfere constructively to produce the best focused image. And there you see it. So in March we saw this, a bright star seen with James Webb, perfectly focused, and every astronomer got very excited on Twitter. I should say now, stars are round, everybody. These spikes you see, they're called diffraction spikes. Every telescope has them, every camera has them. They're caused by the internal optics of the telescope instrument. So those spikes are only a few percent, and this is a very high contrast image here. Those spikes don't really exist, but they look pretty. Now, every astronomer wasn't looking at the star when this was put out by NASA. They were looking at all the little smudges in the background and going, oh, that's interesting. And they're comparing them with previous sky surveys and saying, oh my God, this is very, very deep, and it was. Okay, so then we had to wait until July because the super secret NASA operation went into place to image the first objects and keep them secret and not release them until a special media day. And I guess NASA's earned it, having built this for 30 years. So Joe Biden decided to unveil the first image on 11 July. I was watching this news conference very late at night, and it's like, President was talking, blah, blah, blah. It's like, we want to see a zoom in on that image in the background. We can't see it. But we did see it in the end. Well, so this was the famous first image. It is the galaxy cluster with the wonderful name S-MAX 0723. I won't get into why it's called that. You can see this image. It's incredible. Every splodge here most of the splodges here are galaxies. You see some very bright stars with the little hexagonal patterns in the foreground. You see a big splodge in the middle. That's actually a galaxy cluster. We have lots of massive galaxies, and then we have loads of little distant universe galaxies in the background here. And there's a lot of what we call gravitational lensing going on, which is a whole another story. So that was the very first image. Next day we saw a few more. This is Stefan's quintet. It's a group of interacting galaxies, 5 of them. This is an awesome image to compare with the previous Hubble data. This is a planetary nebula, Southern Ring it's called, and showing 2 different infrared bands from James Webb. And you can see that we're seeing details like the second star there that weren't seen before in this data. And then here is the Carina Nebula, which is a star-forming region in the Milky Way, where all the brown stuff is gas and dust in space forming stars, and then the stars form and they blow these holes in the gas. So just to the blue light at the top is the radiation from these stars burning out these cavities in the nebula. Now, I'm not going to talk any more about these first images. It's been all over the media for the last 3 weeks. You can read plenty about them. What I'll talk about today is this. So about 1 week before Joe Biden, NASA showed us this on their website saying, data have been taken for the GLASS early release science program. So it's like, oh my God, they've taken our data. But of course, we weren't allowed to see it. So we had to sit there waiting until after Joe Biden, in fact 2 days after Joe Biden, data was taken on June 28th. It was sitting there. We couldn't download it to July 14th when we downloaded it. And we were going, oh, what's it going to show? What's it going to show? So the rest of this talk, we're going to talk a bit about GLASS, that early release science program that our team at University of Melbourne were very fortunate to be a part of, and what we learned from GLASS. But first, let me just set the scene. So what was the target for this GLASS program? So the target was this thing. This is another wonderfully named object, ABEL 2744, the 2,744th galaxy cluster that George Abel discovered, looking at photographic plates. NASA recently renamed it Pandora's cluster. So what you see there is a giant galaxy cluster. There's 3 or 4 of them actually merging together in the intermediate universe. And there's a huge amount of stars and galaxies and gas there. And that cluster was the first target for this early release science. We pointed James Webb at the centre of the cluster down here, bottom left. And we also had these parallel fields up top right. Because James Webb has a number of cameras, as I mentioned before. One great thing is you can use them at the same time. So you can stare at neighbouring fields while you're doing one program. So we got the data. Our team has been involved in about 20-odd different science projects over the last few weeks. We're going to tell you today about 2 of them. And the 2 we're going to tell you about are using these parallel fields, which are basically deep fields looking at a random part of the universe. So this background image here is from the ground. It's from the Dark Energy Survey. This is a ground-based 4-metre telescope. So I can show you what the Webb does. Here's the Webb image of that part, and then that part. So that's what Webb does. And you can see they're not really blank fields. There are countless numbers of objects there. Just about everything in these images are distant galaxies. And you can sort of stare back and forth and compare them for hours, actually, or weeks in my case. So what we're going to do now is we're going to zoom in on particular objects and talk a bit about the science. So we're going to start by going to the very, very, very beginning of time. We're going to talk about James Webb's first view of the first galaxies. And these were actually found like 2 days after we got the data because the data was so awesome. So I'm going to hand over now to Nicha, who is a core person involved in that particular science project, who's going to tell you about these objects. Nicha.
So, hi Hi, everyone. So before I talk about the baby galaxies at the beginning of the universe, let me first tell you about a brief history of our universe first. So based on what we understand, the universe starts with being infinitely small and infinitely dense. After what we call the Big Bang, it has been expanding since then. And actually, we can relate the size of the universe at any moment of time with the concept of redshift that Karl just mentioned, with the factor of redshift plus 1. For example, at redshift 9, the galaxy at the time was 9 plus 1, or 10 times smaller than the current size in terms of radius. The initial state of our universe was full of fuzzy dense stuff, fuzzy hot stuff such as protons and electrons and light particles. At 400,000 years old, the universe has expanded and cooled down enough such that those protons and electrons can bound to each other and form hydrogens. After that, the universe was full with hydrogens and something called dark matter. And since both hydrogen and dark matter have mass, so they attract to each other and start to form clumps of gas that eventually will turn into stars and galaxies. Our galaxy, the Milky Way, actually formed its first star around when the universe was just a little bit less than 1 billion years old. But our sun, or our solar system, which is one of 100 billion stars in the Milky Way, actually formed about 4 billion years ago. So it's actually quite late in the game, which is actually good for us life forms. So now in terms of observations, we have observed millions of galaxies already using the ground-based telescopes. But at higher redshift, we have been relying on the Hubble telescope. So anything from when the universe was 1 billion to 4 billion years old. As you can see here, we still have a big chunk of the universe that we really don't have any observations. And therefore, we cannot confirm our models of the universe. And this is one of the main signs of the James Webb Telescope, which is to look for these baby galaxies at the beginning of the universe. Actually, maybe not to the first 100 million year old, because we expect nothing other than hydrogens there, but anything after the first stars form. All in all is to confirm that our understanding of this timeline is not wrong. I have to mention that every time we have a new instrument, our understanding of this timeline of the universe improves. Before Hubble, we thought that the universe was idle for a very long time and did not form any star for the first billion years of the universe. But now we know that this timeline is wrong because we have seen so many stars, many galaxies before that. But we still don't know if this is not wrong. And we have to wait for the confirmation from the James Webb data or a modification of this timeline. So how do we observe? Sorry, I need to go back. So far, James Webb have observed about 6 or 7 images of the extragalactic field. And here I'll show you 2 of them. One is the one that Joe Biden released, which is at the center of a galaxy cluster. And the second is the blank field that our team obtained. And what I mean by blank field is that if we were to look at this patch of sky with our eyes or with a small telescope, it would appear totally dark. And it is which is a perfect spot to search for galaxies that are very, very far away, because they will not be blocked by these foreground bright nearby galaxies or for the stars in our own Milky Way. So how do we search for those galaxies that are very far away? We actually, first I have to tell you that in the, when we take the image of this field, the telescope doesn't work like our phone camera where we just click and then we obtain a nice colored image. We actually have to observe them obtain monochrome images several times, but each time we use different filters. So here we use 7 filters ranging from 900 nanometers to 4400 nanometers. And based on these images, we look for galaxies with a unique characteristic, that is that galaxies that disappear in the shorter wavelength band and appear in the longer wavelength band. And why is that so? Because we know that galaxies at the beginning of the universe, or those galaxies would be forming a lot of stars, and they would contain a lot of hot young stars. And we know that something that is very hot would appear to be blue, just as when you look at the fire from the gas stove, the inner blue part is hotter than the outer red part. In fact, that these galaxies, these stars are so hot such that if we were to stand in front of it and with a prism in hand, the brightest part of the brightest light would be somewhere around 100 to 200 nanometers, and which is bluer than the blue color that our eye can see, which is at 500 nanometers. But actually, this is not what the light that would come out of the galaxies, because galaxies at those times are full of hydrogens, either both inside the galaxy itself and outside the galaxies. And the special characteristic of these hydrogens is that it would absorb any light that is shorter than 120 nanometers. So anything below that would appear totally dark. However, our telescope is not right in front of those galaxies. Our telescope is in fact 13 billion years apart from the galaxies. And all the lights are shifted into the infrared bands that we see. And this is essentially how we detect those first baby galaxies. And this is one of the galaxies that we found within 2 days of the data release. And this is a galaxy at redshift 12, which is when the universe was only 370 million years, or like 13.5 billion years ago. In this image on the right, this galaxy appears just as a tiny, tiny dot on the edge of the image over there. And next, I'll show you how revolutionary the James Webb Telescope is. Each dot in this plot is a galaxy that we have discovered with the Hubble telescope. Their redshifts are marked by the x-axis. The y-axis just shows how bright they are. And as you can see that even though we have been observing with Hubble for about 30 years now, we only have a few data points above redshift 9. But based on just 6 or 7 images from the James Webb, with the observing time of total of just a few days, we now have opened up a new window into the universe. And these are marked by the red dots here. And this is just for a few days. And I'm sure that, and you can imagine that within the next few years, this plot will fill up with red dots. And what do we learn from these galaxies? How do we, what information can we get? Turn out that we astronomers are very good at extracting information from the data. So just based on these images alone, we can actually estimate their physical properties, such as mass, how many stars are there in that galaxy, how old are the stars, how much stars are they forming per year, and once we have a lot of number, we can get number density, or how many are there in the universe. And based on these physical properties, we then can infer the answer to the bigger questions, such as the timeline of the universe at the beginning. Yep. So next, I'll hand over to Colin to talk about galaxies at adolescent stage.
Thanks, Nicha. So I'm quite lucky. I get to use one of the best things about astronomy, which is pretty pictures. I've been looking at galaxies that are a little bit older than those tiniest, very first galaxies, a couple of billion years later and on, to see what we can learn from the shape and the colour of those galaxies. Both of these properties are very closely related to the astrophysics of the galaxy, what's going on, and how those galaxies came to look like the ones we see today. And I'll go into a little bit of the detail about what these actually mean. So these are Hubble Space Telescope images. If we look out at the local universe, at the galaxies that are near to us, we see many galaxies that look like this. On the left is a spiral galaxy. On the right is a barred spiral galaxy, it's called. Our Milky Way looks something like that one. And we also see a lot of galaxies that are big blobs like this, which is an elliptical galaxy. Some of these can be extremely massive, the biggest galaxies in the universe. And going back as far as the 1920s, Edwin Hubble, after whom the Hubble Space Telescope is named, of course, came up with a classification system to try and put some order onto all of these different shapes of the galaxies that we see in the local universe. Those different types of spiral galaxies, the elliptical galaxies, and that way people can start to think about how they come to be, how these galaxies evolve, which galaxy type gives way to the other types. But it's still a mystery exactly when do these orderly classes of galaxy come to be? When do we get from those very early blobs, the very first galaxies in the universe that are patchy and made of gas, become these sorts of beautiful structures that we see in the local universe today? So here's a few more images of galaxies that are relatively nearby to our own. At the top are elliptical galaxies, at the bottom are these spiral galaxies. And one thing that's very obvious from these is that they're different colours. So as Nicha touched upon, this is a property of the stars that make up the galaxy. And you can think of it like this, that the older stars in the galaxy, which happen to be smaller, and maybe something like our own sun, are red hot. So just as if you took a blowtorch to a piece of metal, it would heat up to a few thousand degrees and start to glow red. Whereas if you kept the blowtorch on until it became blue hot or white hot, then it would look different in colour, and that's exactly the same for stars. Stars that are bigger burn brighter and hotter, but they don't live as long. So to have lots of very hot blue stars, the galaxy has to be forming stars to keep replacing them as they die. The biggest, hottest stars can die in as quickly as a few million years, whereas a star like our sun will last for billions of years, and stars can last a lot longer than that. So when you're looking at the colour of a galaxy, it's telling you a lot about how old it is and what kind of stars are there. However, we don't get a pretty picture like that when we take an image from a telescope. Here's what an astronomer sees when they actually get that data that Karl was saying we're all so excited to get. And this is the sort of tool that an astronomer might use to open one of these images that we get from a telescope. This is some of our James Webb data. So the first thing that pops out is there's some blank areas and some sort of scratchy parts. Those are just where it's off the detector, or it's right on the edge of the detector. But the next thing that you see is, as with Nicha's images she showed, it's black and white. It's sort of a grayscale image. It's not really like, we don't think of this really like a normal photograph. Each one of those pixels is actually telling you how many photons per second it's getting. Like, it's a physical measurement of how much energy we're getting from the galaxy. So how you would view that and how you would think of colour is not entirely straightforward. Like, here's a couple of galaxies from our James Webb data. You can use all sorts of different schemes that you want to visualise, what's going on there, how bright the galaxy is in a particular wavelength. You can apply a colour scheme to highlight particular details, or you can make certain parts brighter and certain parts dimmer to see more or less detail. That's something you can use to try and get an explanation scientifically, but what does it actually mean for colours that we would see, and colours in those beautiful images that we saw from Joe Biden onwards? So we've heard before that James Webb isn't giving us data just from the infrared, but into all these little different slices of the infrared. 7 of them, in fact. And if we look at one of our galaxies, we look at these galaxies in those different slices, it will look different. So you can see that on the left, in the bluest end of those filters, the galaxy is quite dim, but you can only see a few little clumps and bumps in there. Whereas when you go all the way to the reddest filter, that is the furthest into the infrared, they both look very, very bright. So this is a hint about colour. It's very bright in the red, but not very blue. So we can make a colour image just the same way we would use a photograph, because the human eye is sensitive has 3 different types of sensors in it. So when we see things, or when we make a photograph, we take something that represents the red part, something that represents the green part, and something that represents the blue part, just directly related to the sensors in our eye, and we combine those together and we get a colour image. How strong something is in the blue part compared to the red part is going to determine how blue a part of that image looks, or indeed a part of something that we see with our eyes looks. So when we have our 7 different slices of the infrared, we can call one of them the red part, like the red dog, one of them the green part, and one of them the blue part, and combine those together to make a colour image that is something that our eyes can understand. So here's our 2 galaxies again. So we take 3 of those different images from the James Webb, and we take the red, we add the green, and we add the blue, what we're calling the blue part, and we get something that's in colour. But what do these colours actually represent? Because everything in the infrared is completely invisible to the human eye. So what does that actually, how real are these colours? Well, there's one thing that we can do for the very first time with James Webb, which is we can look at galaxies that are very far away, but look at the parts of the electromagnetic spectrum that are just like our eyes would see, the visible parts, once they've been stretched all the way out into the infrared. So what's happening here is that we've got 3 parts of the visible spectrum that are quite close to what you would see with your eye, where at different times in the universe's history, those parts of the visible light would look like once redshifted into the infrared. So we can take one of those snapshots, see where they line up with those 7 James Webb filters we have, and use those for the red, green and blue channels in our image. And if we do that with our 2 galaxies, we actually see something like this. They're quite red. And if you remember back to those images I showed at the start of the local universe, most of the spiral galaxies are very blue. So already that's like a very interesting result. What's going on here? Why do these spiral galaxies seem so red? Not like what we see around us. So that's a few hints from colour. So what about shape? Before we got our data, we did a few simulations. We took some images of local galaxies, some of those nice big spiral galaxies, and tried to figure out what they would look like if we viewed them with the James Webb Space Telescope from the very, very early times in the universe. So if we take something that's nearby when the universe is 13.8 billion years old and moved it so far away to when the universe was 6, 4 or 3 billion years old, what would it look like in James Webb? And because the resolution is so great, even though they get much, much smaller and dimmer and into the infrared, we'd be able to see a lot of that detail with James Webb. So if these galaxies that look like the ones today are actually there at these early times, we should be able to detect them. And here's a better illustration of why James Webb is so important. So here's the Stephan's Quintet. This is the Hubble Space Telescope image that we've had for quite some time. Here's the James Webb infrared image of Stephan's Quintet. But if we zoom in on just one tiny little corner here where there's a few galaxies, we can see that here in the Hubble image, you just sort of see mostly these blue dots. And those are the very bright blue, actually ultraviolet areas where stars are forming. But as we go to the infrared with the James Webb Space Telescope, all this extra detail emerges. And what that actually is all of the stars that are older, all of these red hot stars. And you can actually see it's quite dramatic here that there's a whole bunch of galaxies around this middle one that you can hardly see it all in the Hubble Space Telescope. But once we look at it through the James Webb's view onto the infrared, all this structure emerges. All of these older red hot stars appear. So what might seem sort of clumpy and scraggly in the Hubble Space Telescope imaging suddenly has all of this rich structure that we couldn't see before. Here's another example, just one little example from our data. This blobby structure here is what we see in the bluest part of the infrared spectrum that we got, but when you look at it in the reddest part, it has a completely different shape. All of this extra structure is revealed, and this is well beyond what we could ever see before with Hubble and certainly from the ground. So taking those two things, being able to make pretty colour pictures to see what shapes the galaxies are, and being able to see all of this structure that we couldn't see before, we made what we called an atlas of the early universe. And we arranged our galaxies by how old they are, or rather how old the universe is here, and how massive they are. You can certainly see there's some trends. As the universe ages, they clump together and get bigger. And as they get bigger, they have more structure, and some of these spiral arms and things like that start to appear. And so one interesting part of this image is here, where the universe is only a couple of billion years old, and we're already seeing these big spiral galaxies, some of which are as massive as the Milky Way galaxy is, 11 billion years later. And this is a bit unexpected. So just from that one image, we're already having to rethink. Maybe the Hubble tuning fork applies at much earlier times than we thought that it might have. And so finally, we could actually recreate now this Hubble tuning fork classification scheme using our own galaxies from the James Webb Space Telescope. We can see ellipticals, we can see spirals, we can see weird clumpy things that are still in the very early stages of forming. But it's really exciting to be able to see all of this structure emerging in the universe at an early time where we thought maybe everything is just looks like clumps and is irregular. But now we can see all of this beautiful structure in these beautiful colours for the very first time. Very exciting. And I look forward to comparing this to what the theorists who are making simulations of the universe, when did they think these sorts of beautiful galaxies should be forming? And I'll hand it back to Karl.
Thanks, Colin. So just to finish off, one thing I want to emphasise, we've only had data for like 4 weeks, okay? This is not the end, it's not even the end of the beginning, right? This is just like the first tiny step with doing science at the James Webb Telescope. I showed you earlier this image of our field, Pandora's cluster. This small patch of sky is what all this science has been done from. If we zoom out, we can put this into perspective. So this shows the moon in the sky for scale, and those red boxes on the left, that's our fields that James Webb observed. So it's only a tiny fraction of this area, and in fact, even the field size of the moon is only like 1/40,000th of the entire sky. So there's a huge amount of sky that hasn't been looked at yet by Webb. So I want to show one very complicated slide to finish off. And I have motivation here, which is that everything I've shown you so far has been images. But James Webb has a capability to do what we call spectroscopy, where we take the light and we dissect it into wavelengths. This is shown here. This is a bit complicated to explain, but each trace is like a spectral trace of a different galaxy. We got this data like 2 weeks ago. We're splitting the light out into colours. You can think of each one as like a DNA fingerprint of a galaxy. So as we go along the trace, we're actually measuring the energy at different wavelengths, and we can use that to measure the redshift very precisely, the chemical composition, the amount of different elements. We can measure the amount of carbon, the amount of oxygen. We can see how the matter universe is being built up with data like this. And this is just the first part of this data. So James Webb has been taking data for 4 weeks. It's designed to have a 10-year lifespan. The orbit insertion was perfect, so it's probably got to have a 15 to 20-year lifespan. So it's only a few weeks. I think the discoveries we'll make in the next 15 years are just too enormous to contemplate. I think it's going to really revolutionise that picture of the early universe. And we're all looking forward to the next surprises. So thank you all for coming. It's been a pleasure to give this National Science Week talk. And thank you all for coming on behalf of myself and the team here.
All right, that was so exciting. I have more questions than answers now, but I work with them, so I can ask questions anytime. So if you have any questions, please put your hand up. We'll try to accommodate 2 or 3 questions because we're running a bit behind schedule.
Hello. This is a completely layman's question that you as scientists might think is really stupid, but I'm just fascinated to know because I think about it all the time. You're looking at a galaxy that is billions of years old. Where could that galaxy be now?
Should I take that one? Yeah, we think that galaxies in the universe don't disappear. So when we see a galaxy like 10 million light years away, where a galaxy is now, it would have redshifted past where we can observe. We can no longer observe that object. It's gone too far away in the universe. So we have to make an analogy between average properties of the universe. We're looking at the average of things nearby and the average of things far away. But you can't see the trajectory of an individual galaxy across time. Does that make sense?
Yes.
So I was going to ask, why do you usually compare the James Webb to Hubble Telescope images?
Well, because it's the new thing. We compare because Hubble is still our only way of doing visible light imaging. So by comparing the visible and the infrared, we can get even more information. But it is difficult because often James Webb can see things that Hubble can't even see at all. So that makes it a bit complicated.
G'day. I was just going to ask, with L2, that Lagrange point 2, how the James Webb Telescope is held in balance there. Has anything else, like asteroids or anything, been caught in L2 and is stuck there as well?
Yeah. So yes and no. L2 is a stable point around which Webb can orbit. It's a semi-stable orbit, which means every couple of months they have to burn the rocket a little bit to keep it from being pushed away from L2. Interstellar junk doesn't tend to accumulate there because of that, but there is stuff in the solar system anyway. The telescope's been impacted by at least one major micrometeoroid in the last few months, and so that's always a concern. There are several other spacecraft at L2 in the same orbits, the European Gaia mission, for example. So it's actually quite a popular orbit.
Maybe one last question. And,
Just before we do that, I just wanted to quickly plug all the prizes that we're giving away tonight. So 2 of our PhD students made this really awesome colouring in book, Women in Physics. So if you want to support their leadership journey, they're saving up money so that they can go to Antarctica on a leadership course. You can grab your copy of Women in Physics colouring in book on amazon.com.au. Here's a free version for you. We've got a free app that you guys have got the little mini VR viewer for. So that's the Cyber app, Science in Virtual Reality. That's available free on the App Store for your tablets and mobile phones. And person down the front, you scored a copy of Astronomy Sky Country. So the last lecture in our series was from Crystal DiNapoli. She's an Indigenous astronomer, and she and Colin have written a book about their astronomy journey. So you can grab copies of all of those and support all of those things, and we'll just go to the last question now. Sorry, my name's Lisa. If you are on the email list, you've been getting emails from me. If you want to join the email list, I'd love to email you. Let's go last question over here.
Thank you. That was a very interesting and amazing talk. I was just, in the beginning, you spoke a bit about the amazing feat of it unfolding out once it was launched, and I was wondering if you could speak a little bit about any of the contingency plans that were put in place in case something went wrong, and did they use any of those contingency plans?
Yeah, well, there were no contingency plans. So everything had to work just right the first time. So that's what, $10 billion gets you, making sure there are lots of fail-safes. So as you might know, when Hubble Space Telescope was first put up into low Earth orbit, there was actually a problem with the optics. So the pictures it took were basically all blurry. They were able to send astronauts up in the space shuttle to go out and repair the Hubble Space Telescope. So now we got 30 years of all of those beautiful images. But if anything goes wrong with the James Webb Space Telescope, it is way, way further away than a human astronaut has ever been, and will probably go for quite some time. So everything just had to work perfectly, way out there, 1.5 million kilometres away.
Yeah, unfortunately, we had to cut it over there. But if you have any questions, all of us will be in the front. So please do come down and chat with us. We'll be here until you all leave. So there's no time constraints. And just before we finish, I want to remind you about the next talk by Rebecca Allen in September 30th about the Australian involvement in the space industry, which will be a really cool talk to come as well. And if you need to be put in your email list, just talk to Lisa over there. All right, thank you very much for coming, and hope you have a nice flight back.